Welcome, I am Izagani Ibarra B. Heniza. This video is all about sampling of continuous time signals and aliasing. Sampling of continuous time signals and aliasing. Here are the learning outcomes. After watching this video, you will be able to, number 1, identify the basic parts of the A to D converter block diagram and state the operation of each. Number 2, express the mathematical expression of the continuous time signal x of t in terms of its discrete equivalent x of n. Number 3, solve for the quantization step to be used for the quantized values x sub q of n of the discrete time signal x of n. Number 4, solve for the quantization error e sub q of n for rounding and check if it is within the limits. Number 5, determine the number of bits to represent each discrete value x sub q of n for a given quantization level L. Number 6, illustrate the waveforms of x of t, x of n, and x sub q of n. Number 7, discuss and illustrate the process of impulse train sampling. And number 8, illustrate the effect of sampling at omega sub s greater than twice the value of omega sub m, omega sub s equals twice the value of omega sub m, and omega sub s less than twice the value of omega sub m. The analog to digital converter system has 3 basic components. The first stage is the sampler. It converts an analog signal, x sub a of t, to a discrete time signal, x of n. This discrete time signal is then fed into the quantizer to make its values discrete. It is then called a quantized signal, x sub q of n. The last stage, which is the coder, converts this quantized signal into its binary equivalent, which is called the digital signal. With the current advancements and utilization of digital systems, there is a need to convert continuous time or analog signals to digital signals. The first step is sampling. In sampling, we take samples of the analog signal at periodic discrete time instants. This is done by using a sampler. A sampler is a subsystem that extracts samples from a continuous time signal. It produces samples equivalent to the instantaneous value of the continuous time signal at the desired points. The sampler can be represented by a single pole, single throw switch. The SPST switch is turned on and off periodically at a rate of f sub s. The input is a continuous time signal and the output is a discrete time signal. When the SPST switch is open, there is no output x of n. When the SPST switch is closed, the instantaneous value of the continuous time signal is equal to the output values of the discrete time signal. An example of a continuous time signal is shown on the left. Suppose this continuous time signal is sampled at equally spaced periods, t, 2t, 3t, and so on. Its discrete time equivalent is the one shown on the right. X of n will have values on these time periods, but between these time periods, for example between t and 2t, x of n is unknown. After converting the continuous time signal to discrete time signal, the values of x of n are then converted to discrete values. This is called quantization. In quantization, there is a finite set of possible values, which is defined by the quantization step delta. In this figure, the one on the top is x of n, and the one at the bottom is the quantized signal x sub q of n. The quantization step delta is 0.1. During quantization, the values of x of n will take on the discrete values defined in increments of 0.1. Quantization can be done through truncation or rounding. To determine the quantization step, we will use this equation: delta equals x sub max minus x sub min all over L minus 1, where delta is the quantization step, x max minus x min is the dynamic range of the signal, and L is the number of quantization levels. The more quantization levels, the better, because delta will be smaller, hence more discrete levels for the values. This will ensure that the quantized value will more likely be near its original analog value. Let us have an example. For the signal x sub a of t equals 0.9 raised to t, the maximum value is 1 and the minimum value is 0. And the number of quantization levels, L, equals 11. Find the quantization step. Using this formula, delta is equal to 1 minus 0 all over 11 minus 1, which is equal to 0.1. This is the tabulated result. The values of the discrete time signal and the quantized values are determined for n from 0 to 9. In truncation, the amount in excess of the discrete value is cut off. For example, at n equals 3, x of n is equal to 0.729. It is above the discrete level value of 0.7. The excess of 0.029 is then cut off. In rounding, the values are just rounded off to the nearest discrete level value. The last column is the quantization error for rounding. This is important because this will determine if the quantization is within the range. The quantization error for rounding is then checked by using this range. Each of the e sub q of n from the previous table falls within this range. After converting the analog signal into discrete time, discrete value, it will be converted to binary values. We will use this condition to determine the minimum number of bits that will be used to represent each discrete value. For 11 quantization levels, at least 4 bits are required to represent each discrete level. A band-limited signal is a signal in which its Fourier transform is non-zero only for a range of radiant frequencies, from negative omega sub m to positive omega sub m. It is 0 elsewhere, and positive omega sub m is the maximum frequency contained in the signal. It is useful in determining if the analog signal can be accurately reconstructed from its samples. Sampling of continuous time signals can be carried out by impulse train sampling. A message signal x of t is fed into a sampler or a multiplier. The instantaneous values of x of t are taken at equally spaced time periods, defined by t. T is the sampling period or the sampling interval. This is done by also feeding a periodic impulse train into the sampler. The periodic impulse train is defined by this equation. P of t equals the summation from n equals negative infinity to positive infinity of Dirac delta of t minus n times t. If n equals 0, delta of small letter t minus 0 times capital T is equal to delta of t. This is the unit impulse present at t equals 0. If n equals 1, delta of small letter t minus 1 times capital T is equal to delta of small letter t minus capital T. This is the unit impulse present at t equals t. If n equals negative 1, delta of small letter t minus negative 1 times capital T is equal to delta of small letter t plus capital T. This is the unit impulse present at t equals negative t. The same is applicable for all values of n from negative infinity to positive infinity. To illustrate the spectrum of the sampled signal x sub p of omega, its Fourier transform must be derived. X sub p of t is equal to x of t times p of t. Getting the Fourier transform of x sub p of t, we have x sub p of omega equals 1 over 2 pi times x of omega convolved with p of omega. The Fourier transform of the impulse train is p of omega equals omega sub s times the summation from n equals negative infinity to positive infinity of delta of omega minus n times omega sub s. Continuing, we have x sub p of omega equals 1 over 2 pi multiplied by x of omega convolved with omega sub s times the summation from n equals negative infinity to positive infinity of delta of omega minus n times omega sub s. X sub p of omega equals omega sub s over 2 pi. In this case, omega sub s is factored out, times x of omega convolved with the summation from n equals negative infinity to positive infinity of delta of omega minus n times omega sub s equals 1 over t times the summation from n equals negative infinity to positive infinity of x of omega convolved with delta of omega minus n times omega sub s. Notice here that the term omega sub s over 2 pi is changed to 1 over t. And finally, we have 1 over t times the summation from n equals negative infinity to positive infinity of x of omega minus n times omega sub s. Let us expand the Fourier transform x sub p of omega using n from negative 2 to positive 2 for simplification purposes. For n equals negative 2, the term is x of omega plus 2 omega sub s. For n equals negative 1, the term is x of omega plus omega sub s. For n equals 0, the term is x of omega, which represents the spectrum of the original message signal. For n equals 1, the term is x of omega minus omega sub s. And for n equals positive 2, the term is x of omega minus 2 omega sub s. For negative values of n, these are the spectra of the original message signal shifted to the left. And for positive values of n, these are the spectra of the original message signal shifted to the right. In the diagram, it can be seen that there is no overlapping between adjacent spectra, as shown. Because the sampling frequency is greater than twice the highest frequency of the message signal. This is what we call oversampling. While in this diagram, adjacent spectra touch. because the sampling rate is equal to twice the highest frequency of the message signal. Twice the highest frequency of the message signal is called the Nyquist rate. Lastly, when the sampling rate is less than twice the highest frequency of the message signal, overlapping between adjacent spectra will occur. This is undesirable because the message signal cannot be extracted from its samples. This is called undersampling. The sampling theorem is the main basis in signal theory. The sampling theorem states that a continuous time signal can be derived from its samples if the sampling frequency used is omega sub s greater than twice the value of the maximum frequency contained in the signal. Summarizing the different sampling rates. For oversampling, we have omega sub s greater than 2 omega sub m. Expressing it in terms of frequency, we have 2 pi f sub s greater than 2 pi f sub m. F sub s is greater than 2 f sub m. This is allowed because no overlapping occurs. For the Nyquist rate, omega sub s equals 2 omega sub m. 2 pi f sub s equals 2 pi f sub m. Therefore, f sub s equals 2 f sub m. This is allowed but not preferred because touching between spectra occurs. And also, the Nyquist rate defines the maximum period between samples. This is t equals 1 over f sub s equals 1 over 2 f sub m. For undersampling, we have omega sub s less than 2 omega sub m. 2 pi f sub s is less than 2 pi f sub m. Therefore, f sub s is less than 2 f sub m. This is not allowed because overlapping between spectra occurs. Let us have an example. Find the Nyquist rate and Nyquist interval. For the given analog signal, x of t equals cosine 1000 pi t plus sine of 2000 pi t. For the first term, we have cosine 1000 pi t. Therefore, omega sub 1 equals 1000 pi. For the second term, we have sine of 2000 pi t. Therefore, omega sub 2 equals 2000 pi. In this case, omega sub 2 is greater than omega sub 1. To get the maximum frequency, we have omega sub m equals omega sub 2 equals 2000 pi radians per second. Expressing it in terms of hertz, f sub m is equal to 2000 pi divided by 2 pi equals 1000 hertz. Determining the Nyquist rate, we have f sub n equals 2 f sub m equals 2 times 1000 hertz equals 2000 hertz. This is the Nyquist rate. Determining the Nyquist interval, we have t equals 1 over f sub n equals 1 over 2000 hertz equals 0.5 milliseconds. It means that the maximum interval between samples should be 0.5 milliseconds. Next example, express the continuous time signal in terms of its discrete time equivalent. We have x of t equals cosine 1000 pi t plus sine 2000 pi t. The first term, we have cosine 2 pi times 500 t. 2 pi ft equals 2 pi times 500 t. Therefore, the frequency in hertz of the first term is 500 hertz. For the second term, we have sine of 2 pi times 1000 t. Therefore, the frequency of the second term is 1000 Hz. A band-limited signal can be filtered out from the spectra of its samples using a low-pass filter. This is called the recovered signal X sub r of t, and its spectrum represents the spectrum of the original message signal. In this case, there should be no overlapping in order for the spectrum of the recovered signal to fall into the passband of the filter. Let us now analyze the spectra when the frequency omega naught changes while the sampling frequency omega sub s is fixed. Consider the signal x of t equals cosine of omega naught t. The frequency domain representation of x of t is shown in letter A. The spectrum includes also negative omega naught for completeness of analysis. In letter B, the signal is sampled at 6 omega naught. Therefore, it follows the sampling theorem. Take note that the sampling theorem states that the signal should be sampled at a rate of more than twice the highest frequency component of the signal. It will then generate a lower frequency component omega sub s minus omega naught for a center frequency of omega sub s. It does not fall in the passband of the filter, therefore overlapping of spectra did not occur. The same case also happened in letter C, in which the signal sampled at 3 omega naught. Letter A is still shown here for reference. In letter D, the signal is sampled at 1.5 omega naught. Therefore, it does not follow the sampling theorem. Take note that the sampling theorem states that the signal should be sampled at a rate of more than twice the highest frequency component of the signal. In this case, it is sampled less. It will generate a lower frequency component of omega sub s minus omega naught for a center frequency of omega sub s. It will fall in the passband of the filter. Therefore, overlapping of spectra has occurred. The same case happened in letter E, in which the signal is sampled at 1.2 omega naught. These next illustrations show the time domain representation of the previous example. The solid line represents the original analog waveform sampled at 6 omega naught. The arrows represent the samples and the dashed lines represent the reconstructed or the recovered waveform. The waveform is accurately reconstructed from its samples because it is sampled at greater than 2 omega naught. Therefore, aliasing does not occur. This waveform is also accurately reconstructed from its samples because it has been sampled at 3 omega naught. Therefore, aliasing does not occur. This waveform is not accurately reconstructed from its samples because it has been sampled at 1.5 omega naught. The waveform at the bottom is an alias of the original signal. This waveform is also not accurately reconstructed from its samples because it has been sampled at 1.2 omega naught. The waveform at the bottom is an alias of the original signal. Let us have another example. A signal x of t with Fourier transform x of j omega undergoes impulse train sampling to generate x sub p of t equals the summation from n equals negative infinity to infinity of x of n times t times delta of t minus n times t. where capital T is equal to 10 raised to negative 4. For the following x of j omega, can x of t be recovered? Letter A, the given x of j omega is equal to 0 for the absolute value of omega greater than 5,000 pi. The Nyquist rate for the given signal is 2 times 5,000 pi, which is equal to 10,000 pi. The sampling period must not exceed T max. That is equal to 2 pi divided by 10,000 pi, which is your Nyquist rate. T max is equal to 2 times 10 raised to negative 4 seconds. Since t equals 10 raised to negative 4 seconds is less than t max equals 2 times 10 raised to negative 4 seconds, x of t can then be recovered from x sub p of t. For letter B, the value of x of j omega is equal to 0 for the absolute value of omega greater than 15,000 pi. The Nyquist rate for the given signal is 2 times 15,000 pi equals 30,000 pi. The sampling period must not exceed T max. T max is equal to 2 pi divided by 30,000 pi, which is your Nyquist rate. T max is equal to 0.66 times 10 raised to negative 4 seconds. Since t equals 10 raised to negative 4 seconds is greater than T max equals 0.66 times 10 raised to negative 4 seconds, x of t cannot be recovered from x sub p of t. Another example. Consider the analog signal x sub a of t equals 3 times cosine of 100 pi t. Letter A, determine the Nyquist rate. X sub a of t equals 3 times cosine of 2 pi 50 t. This is the factored out version of our given signal. Therefore, f, or the frequency, is equal to 50 Hz. The Nyquist rate is then computed as f sub n equals 2 times 50 Hz equals 100 Hz or 100 samples per second. For letter B, the signal is sampled at a rate of f sub s equals 200 Hz. What is the discrete time signal obtained after sampling? The normalized frequency is equal to capital F divided by f sub s. F is the frequency, which is equal to 50 Hz. F sub s is the sampling rate of 200 Hz. We have 1/4 cycles per sample. We have x of n equals 3 times cosine of 2 pi fn. We will just replace the small letter f here by the value of the normalized frequency f. So therefore, x of n is equal to 3 times cosine of 2 pi times 1/4 n. We have x of n equals 3 times cosine pi over 2n. For letter C, the signal is sampled at a rate of f sub s equals 75 Hz. What is the discrete time signal obtained after sampling? This item is similar to item B. First is we will get the normalized frequency small letter f. We'll just plug in the values. F is 50 Hz. F sub s is now 75 Hz, which means that the signal is sampled at 75 samples per second. We have 2/3 cycles per sample. We have x of n equals 3 times cosine of 2 pi fn. And then we're gonna plug in the value of f here. So that's equal to 3 times cosine of 2 pi 2/3 n. And we have x of n equals 3 times cosine of 4 pi over 3 n. Omega is equal to 4 pi over 3, so that is also equal to 2 pi minus 2 pi over 3. We can now then replace the 4 pi over 3 term in our equation by this one. Therefore, we have x of n equals 3 times cosine of 2 pi minus 2 pi over 3 n. That's equal to 3 times cosine negative 2 pi over 3n. And further simplifying, x of n is equal to 3 times cosine of 2 pi over 3n. For letter D, what is the frequency f greater than 0 but less than fs over 2 of a sinusoid that yields samples identical to those obtained in part C? So we will use this equation, f equals small letter f times f sub s. F is our normalized frequency and f sub s is the sampling rate. In part C, the sampling frequency is 75. That is why we have f times 75 here. It can be seen that f is equal to 1 over 3 in part C. Therefore, f is equal to 1/3 times 75 equals 25 Hertz. It will have the form y sub a of t equals 3 times cosine of 2 pi ft equals 3 times cosine of 2 pi, and then plug in the value of 25 Hertz here times t. That is equal to 3 times cosine of 50 pi t. Y sub a of t here is our analog signal. If y sub a of t is sampled at 75 Hertz, it will yield identical samples with a signal in part C. Therefore, we can say that a frequency of 50 Hertz is an alias of 25 Hertz for a sampling rate of 75 Hertz. We now proceed to the last example. Consider the analog signal x sub a of t equals 3 times cosine of 2000 pi t plus 5 times sine of 6000 pi t plus 10 times cosine of 12,000 pi t. For letter A, what is the Nyquist rate for this signal? Factoring out the omega terms of all the terms in our analog signal, we have x sub a of t equals 3 times cosine of 2 pi 1000 t plus 5 times sine 2 pi 3000 t plus 10 times cosine of 2 pi 6000 t. We're now going to determine the frequency components in kilohertz of each of the terms. F sub 1 equals 1 kilohertz, F sub 2 equals 3 kilohertz, and F sub 3 equals 6 kilohertz, which is your maximum frequency. We can now calculate for the Nyquist rate f sub n, and that is equal to twice the value of f max. That's equal to 2 times 6 kilohertz, which is equal to 12 kilohertz. 12 kilohertz is your Nyquist rate f sub n. For letter B, the signal is sampled at a rate of f sub s equals 5000 hertz. What is the discrete time signal obtained after sampling? First is we're going to get the folding frequency. The folding frequency is just the sampling frequency divided by 2. So we have 5000 hertz divided by 2 equals 2500 hertz. This means that the highest frequency that can be sampled at 5000 hertz is 2500 hertz. We have the different frequency components. We have f sub 1 equals 1 kilohertz, f sub 2 equals 3 kilohertz, and f sub 3 equals 6 kilohertz, and that is your maximum frequency. We have x of n equals 3 times cosine 2 pi. The f here is your normalized frequency. So for the first term, we have f of 1 kilohertz divided by a sampling rate of 5 kilohertz. And then we multiply n. Plus 5 times sine of 2 pi, the normalized frequency of the second term is equal to the frequency of 3 kilohertz divided by the sampling rate of 5 kilohertz times n. Plus 10 times cosine of 2 pi times the frequency of 6 kilohertz divided by the sampling rate of 5 kilohertz times n. We have x of n equals 3 times cosine 2 pi times 1 over 5n plus 5 times sine of 2 pi times 3 over 5n plus 10 times cosine 2 pi times 6 over 5n. For the first term, we do not have to simplify it because this term is less than pi. While for the second and the third term, we have to simplify it because these terms are greater than pi. Let us now focus on the second term. The second term, omega sub 2 equals 6 pi over 5. So that is less than 2 pi. That's why we're going to express it like so. So omega sub 2 equals 2 pi minus 2 pi over 5. So that is equal to negative 2 pi over 5. For the third term, we have omega sub 3 equals 12 pi over 5. That is greater than 2 pi. Therefore, we're going to express it like so. We have omega sub 3 equals 2 pi plus pi over 5. That is equal to pi over 5. After simplifying the second and the third terms, we can now substitute it to our x of n. So x of n now is equal to 3 times cosine of 2 pi 1 over 5n plus 5 times sine 2 pi times negative 2 over 5n plus 10 times cosine 2 pi 1 over 5n. To simplify x of n, we can combine the first and the third terms since they are similar. That is now equal to 13 times cosine of 2 pi 1 over 5n. And we're going to add this term, so we have plus 5 times sine 2 pi times negative 2 over 5n. Letter C. What is the analog signal y sub a of t that can be reconstructed from the samples if ideal interpolation is used? It can be seen from the expression of x of n below, which is this one, that the frequency components present are only 1 kHz and 2 kHz, wherein the original frequency components are 1, 3, and 6 kHz. Therefore, the recovered signal is y sub a of t equals 13 cosine 2 pi 1 over 5, and then multiply the sampling rate of 5 kHz t minus 5 times sine 2 pi 2 over 5 times the sampling frequency 5 kHz t. Further simplifying, y sub a of t is equal to 13 times cosine of 2000 pi t minus 5 times sine of 4000 pi t. The signal is therefore distorted because it does not represent the original equation of our analog signal.